Okay, so in this video we're gonna keep talking about conservation of momentum, but what we're gonna do is we're gonna look at two-dimensional conservation of momentum. Okay, in the example of an inelastic collision or a two-dimensional inelastic collision and a two-dimensional elastic collision. Okay, so the law of conservation of momentum is not restricted to just motion along a line, right? And so when we talk about a line, means like only horizontal, right, or vertical. All right, so it's not only restricted to that. Um, Many interesting examples of collision and explosions involve motion in a plane, right? So when we call this XY motion, we call it the XY plane. And for both of the, for these, both the magnitude and the direction of the total momentum vector will be unchanged. Okay, so total momentum again is a vector sum of the individual momenta, right? So that's the plural form of momentum. So the total momentum, and I forgot, is conserved only if each component is conserved as well, right? And so what does that mean? Be like px1 initial plus px2 initial plus dot dot dot, depending on how many you have. E is going to equal px final, right? One final. And there's a lot of subscripts here, plus px2 final plus dot dot dot, and you could write the same equation for the y. And again, a lot of subscripts when you do two-dimensional um, collisions. And these all, and I would get these all mixed up. So it's pyf2 1 plus, excuse me, pyf2, right, plus dot dot dot, right? So basically just all the individual components in both directions are going to be conserved, okay? And so really when you do these, right, let's just look at some examples, okay? And so here we have peregrine falcons often grab their prey from above while both falcon and the prey are in flight. Right, so a 0.80 kilogram falcon flying at 18 meters per second swoops down at a 45-degree angle from behind a 0.36 kilogram pigeon flying horizontally at 9 meters per second. What are the speed and direction of the falcon now holding the pigeon immediately after the impact? Right, so this is this is an inelastic collision, because after the collision, the falcon is carrying the pigeon. So basically, and this is where my artistic skills come into play. So here's my falcon. They're going to swoop down, traveling 18 meters per second, right, at 45 degrees. Here's my unsuspecting pigeon traveling at 9 meters per second horizontally. After the collision, right after the falcon grabs the pigeon, they're going to be combined traveling at a velocity at an unknown angle, and we'll call that phi. Okay, actually we can just simply call that theta because we know the first theta. Okay, so falcon, pigeon, right? And so what we really have to do is treat this in two dimensions, right? So we're going to, before, right, our collision, we're going to have a horizontal component, and then after we're going to have before we're going to have vertical, right? I'm going to try to do this colorful, right? And then after we'll have a horizontal, and we'll also have a vertical. Okay? And so if I want to try to keep all this kind of craziness sorted, if we want to, right? So horizontally before the collision, right, before the falcon actually grabs the pigeon, both of them are contributing to the total momentum, right? Sorry, my cosine looks a little weird. My stylus kind of drags a little bit. Okay, so that's our horizontal, right? And now our vertical, note that the pigeon's only going in the horizontal, so that our vertical is only going to be from the falcon, right? And then afterwards, horizontally, we're going to end up with the two masses together times our common, it always does it when I write cosine or when I do anything with s's. Right, so our common velocity and our common cosine, or our common angle, and vertically, right, it's just going to be, and let me make these lowercase f's because I don't want you to get it confused with the falcon before, because I call those capital F's. So this is going to be lowercase f, okay? And so I'm going to do what I'm really going to do. Do some erasing here, because this is the stuff that I'm going to kind of start setting equal to each other now. So what I'm going to do is I'm going to take this equation, set it equal to that. I'm going to take this equation and set it equal to that. And in fact, vertically, this will be negative because the falcon's swooping down, right? And so now I'm going to have, I'm sorry if this is starting to look a little confusing. So now I'm going to have a horizontal piece. So I'm going to have MV, sorry. I'm doing M times V, but this isn't M subscript V. This is MF VF cosine 45 plus MP VP equals MF plus MP V lowercase f cosine our unknown angle. And then I'm going to do M negative MF VF sine theta equals MF plus MP VF sine theta, right? And the way to think about it is these two, what I just boxed, that's like saying VF x and VF y. Okay, and then once I have those, I can do Pythagorean theorem and inverse tangent to find my final velocity, right? And so I know if I do a quick little solving, so I'm just going to do that. So VFX is going to be MF VF cosine 45 plus MP VP divided by the total mass. Okay, and so that's going to be 0.80 times 18 cosine 45 plus 0.36 times 9.0 over 0.80 plus 0.36. Okay, just give me 1 second. I left my calculator at school. And so it's going to be 0.8 times 18 times 0.7071. That's a sine of 45 plus parentheses 0.36 times, sorry. So it's going to be 0.80 times 18 times 45 cosine equals 0.80 times 18 times 45 cosine equals plus parentheses 0.36 times 9 close parentheses equals divided by parentheses 0.8 plus 0.36 close parentheses. So the x component is going to be 11.6 meters per second. Okay, and the y component is going to be VFY is going to be negative MF VF sine 45 over MF plus MP. And so that's going to be negative 0.80 times 18 times sine 45 over 0.80 plus 0.36. This should be easy because the top is only 1. There's no addition or subtraction. So 0.8 times 18 times 0.7071 divided by 1.16. And so this is going to be 8.78 meters per second. It's going to be negative 8.78. So VFY. So to find VF, I'm going to do the square root of 11.6 squared plus negative 8.78 squared. And so I'm going to do 11.6 squared plus 8.78 squared equals square root of that. And so my final velocity is going to be 14.5 meters per second, right, or approximately 15. And then I'm going to do the inverse tangent of my y component over my x component. And it's going to be a negative 8.78. So 8.78 divided by 11.6 equals, and I'm going to do the inverse tangent of that, and it's going to be 37.1 degrees. Right? So the final velocity, right, of our Falcon Pigeon system is going to be 14.5 meters per second at 37.1 degrees below positive x. Okay, so again, they're going to be moving down and to the right. All right, so again, I apologize for all the calculator stuff because I ended up leaving my calculator at school. Okay, and so now here's another one where we have two balls colliding on a table. All right, and so like it kind of breaks it down nice and neat, right? It says 1, draw a vector diagram. 2, calculate the momentum of each ball after the collision. And then the last part is what is the speed of each ball after the collision. Okay, and so kind of initially this is the scenario. So before, right, we have ball A traveling towards ball B. Okay, afterwards they're going to go off. Ball A is going to move up and to the right because it tells us it moves 40 degrees to the left of its original position. And ball B is going to travel down and to the right, okay, because it tells us that it moves to the right of balls A's original position. But what I can do is, if you see what I just draw here, and this is our after side, what I just drew here was the 3 pieces that are going to make up our triangle, or make up a triangle, right? Because we know that the momenta of A and B after have to equal that are before's momentum, right? And so here's A's momentum, here's B's momentum. Now this is not drawn the scale because this is 40 degrees, right? And so this is my 50-degree angle, but if I do a little bit of geometry, this is my 50-degree angle, but that actually makes this a 90-degree angle, right? So my picture's not drawn to scale, right? And so if I want to find the before side, right, the momentum before, right, and in fact, let's do something. Let's do 1 because we have an A, ball B. So P1 is just going to be simply ball A's momentum because ball B is not moving, right? And so we know P1 is going to be 5 kilograms times 3.0 meters per second. And so it's going to be 15.0 kilograms times meters per second. Okay? But notice that basically these two are components of that vector. So if I want to make it look nicer, right? so ball A's momentum is this, or ball A's before, so this is 15, right? And we know this is a 90-degree angle, okay? If this is 40, this is 50, but this is ball B after, right? So ball B final, and this is ball A final, okay? And so I can really use trig here to figure out what are the side, or the momenta after, right? And so what I'm going to do is, so ball A, right, after is going to be our momentum before cosine, because it's the adjacent side of theta, which is going to be 40 degrees. So I'm going to do 15 cosine 40. Okay, and so again, let me pull up my phone calculator. 15 times 40 cosine, and so that's going to be 11.5 kilograms times meters per second. And ball B after is going to be P1 sine of that angle, which is going to be 40. So it's going to be 15 sine 40, or 15 times 40 sine equals 9.64 kilograms times meters per second. And so that answers, this set here answers our second question where it talks about calculating the momenta before. This is our vector diagram, so this is like part A, okay? Now what we have to do is find the speed of each ball after the collision, right? Well, now we have their momenta. All we have to do is really divide. So VA2 is just going to be PA2 over MA, and VB2 is going to be PB2 over MB. And so what we're going to do is we're going to divide 11.5 kilograms times meters per second divided by 5.0 kilograms, because that's the mass of ball A. And so we're just going to do 11.5 divided by 5.0, and we're going to get 2.3. Okay, and then we're going to do for VB2, we're going to end up with, I don't know why I keep writing V there, because I'm just going to do equal signs down. So it's going to be 9.64 kilograms times meters per second over the mass of the ball, which is 4.0 kilograms. Okay, and so we do 9.64 divided by 4, and it's going to be 2.41 meters per second. And so there's the answer to our third part of the question, which is what are the velocities after the collision. Okay, and so that ends the talk about two-dimensional collisions. I know it was a little bit longer because the Falcon pigeon question took a little bit longer, but you know, two-dimensional is going to be a newer topic for, it's not really covered in AP Physics 1. And now the last thing we're going to do is we're going to talk about what are devices called ballistic pendulums, where it brings in energy and momentum again to be able to solve for whatever you need for that, initial velocities, final velocities, and so forth.